of the previous conversation, you know. So we're talking about carboxylic acids, first of all, okay? An example of a carboxylic acid, you can see here, okay? And the reactions that they can participate in, one of them was the reaction with a base, as any good acid would do. And another one that we talked about is esterification, formation of an ester, when the hydrogen from acetic acid leaves and hydroxyl group from an alcohol or phenol leaves, they form water and an ester. So, talked about another example of an ester here, but what's kind of cool is that the smell of a lot of fruits is determined by the esters that are found in them. So for instance, an ester of acetic acid and propanol determines the smell of pears. Acetic acid and pentanol, bananas. Acetic acid and octanol, oranges. Butyric acid and ethanol, pineapples. Now, as a person, I did a synthesis of ethyl butyrate when I was in college, and supposedly it should smell like pineapples. It doesn't, because when you prepare it pure, the smell is so concentrated that it smells pretty much like an organic solvent, like a paint thinner. Okay, it's just a little less pungent, but... Okay, now, with esters of these carboxylic acids, these esters can also be broken down using water. We call it hydrolysis in the acidic environment. So what I want to do, I want to go a little bit back and talk about esterification, okay? And remind you, hear me out, that an ester is formed when an alcohol and carboxylic acid interact, okay? Making sense? So if you look at this reaction that is shown at the bottom of that slide, the arrow that goes from right to left, the arrow that demonstrates what happens when ethanoic acid interacts with methanol, is effectively a reaction of esterification. But the arrow that goes from right to left, esterification. Left to right, acid hydrolysis. Quite a few biological molecules contain different combinations of esters, and understanding that water can break down that ester bond and release individual alcohol and individual carbonic acid is quite important for understanding of the functions of biological systems. But the interesting story here is that esters become an acid and an alcohol when they are exposed to water in an acidic environment. What if you switch acid to a base? In this case, you can get a process of saponification. So for instance, if you take an ester of acetic acid or ethanoic acid and methyl alcohol or methanol, and you expose this ester to sodium hydroxide, what you're going to produce is sodium ethanoate, the sodium salt of ethanoic acid, and methyl alcohol. Does that make sense? So what I'm going to write down to compare is the acid hydrolysis reaction This is water, by the way, HOH. So in acidic environment, this is what you're going to get. You see the main difference, well, as a matter of fact, the only difference between these two reactions is this. See that? Other than that, those reactions actually follow the same mechanism. Okay? Good? So that covers our carboxylic acids and esters, and in order to process a couple more types of organic compounds, we're going to introduce amides. So we talked before about a gas called ammonia, which contains one nitrogen atom and 3 hydrogens. When one or more hydrogen atoms in ammonia are replaced with either alkyl groups or aromatic groups, we have amides. Okay? A lot of biological features of living organisms are effectively linked to amides. For example, you're probably familiar with a color called indigo. It's very intense blue color. It is isolated from some plants here, Indigofera tinctoria, right? This is an amine. Okay? Triple substituted nitrogens. All good so far? Now, classification-wise, amines, pretty much like alcohols, can be classified as primary, secondary, or tertiary. In primary amines, only one hydrogen is replaced by an alkyl or aromatic group. In secondary, 2 hydrogens are replaced, and in the tertiary amine, 3 are replaced. Okay? Good, everyone? Now, it is a bit of a, I believe, because of animation, it appears confusing. But, for instance, this is methylamine, the primary one. This is dimethylamine. And this is trimethylamine. We good so far? Now, a lot of aromatic amines are used in industry. For instance, this amine, aniline, can be used as a dye to color a fabric in relatively deep blue color. Okay? In fact, when I was a kid, I grew up in Soviet Union, so I'm not kidding, jeans was a bit of an issue to find ones. And my brother used to buy pants, cheap white pants, and dye them with aniline. You could buy it at like the store. It was pretty common. Now, line angle formulas, and it also allows us to kind of figure out the names. So how do you name the amines? This alkyl residue has 3 carbons, so it is propane. When we derive the replacement group, the alkyl group from propane, we get propyl. Okay, so this is ethyl propyl amine. Okay, diethyl methyl amine. So far, so good? Anyways, okay. Now, nitrogen in both ammonia and amines has a lone pair of electrons. This lone pair can facilitate the binding of hydrogen ion, turning ammonia into ammonium ion and amine into, replacement ammonium ion. So for instance, methyl amine can accept hydrogen ions from water, producing methyl ammonium ion and hydroxide ion. Can you see that? So a couple of comments. Amines are bases, but they are weak bases. All good? Ammonia is a weak base, and amines as well. Another important thing here, hear me out. They are, yes, can highlight. They are not bases in a Arrhenius way of thinking when, a base is something that dissociates to produce hydroxide and ion. They are bases in Bronsted-Lowry character, when a base is something that can accept a hydrogen. Now, a lot of amines smell. Okay? Now, I need to make a disclaimer. For instance, what we learned now is that amines, they were defined as some hydrogens at the NH3 molecule being replaced by carbons, right? Strictly speaking, this compound is not an amine, okay? It's called pyridine. You don't need to know it for the exam. What I'm trying to say is that in this specific material from the textbook, when they use the word amine, they broadly refer to organic compounds that contain that nitrogen with 1, 2, or 3 carbons connected to it, right? But technically speaking, pyridine is not an amine by chemical properties. It has very different chemical properties. Okay? Now, they are, as we mentioned, bases. So when you cook fish, especially when you bake it, the general advice is to spray the fish with lemon juice. Lemon juice is acid. It neutralizes amines and removes the smell. Okay? Here's your molecular culinary. Right? So, well, nobody asks you to cover your fish with the hydrochloric acid. That would be a bit of an overshoot, but the same idea. Okay? The hydrogen from the acid is taken by and binds to a lone pair on the nitrogen of an amine, forming, in this case, methyl ammonium ion and the chloride ion as well. Okay? So far, so good? I have another example for you, seriously. So this is the primary amine. Do you agree with that statement? This is a secondary amine. All right? What if we take a tertiary amine? Okay? What if we do that? And let's say hydrochloric acid to it. What you're going to get, and the formula, the structural formula that I am about to write is not 100% authentic, but it demonstrates my point. Good? So, this nitrogen is bound to 3 methyl groups and forms not really covalent bond, but kind of a bond with a hydrogen. So how many connections, how many bonds this nitrogen forms? Pretty much 4, right? 3 to carbons and 1 to hydrogen. What is the Greek word? I think it's Greek. For 4. Huh? Quarter. Huh? Quad is Latin. Greek is tetra. Okay? So, this is sometimes called tetrasubstituted. Speaking of quad, another term for this is quaternary ammonia. Okay? When you come home, do you have something like a kitchen kind of like Lysol type of thing in the original bottle? I want you to check. Okay.
Well, I do have the original. I get concentrate.
Sure, yeah. Doesn't matter. But read the main acting compound. It's going to be something, a bunch of names of organic substitutes, and then ammonia. Quaternary ammonia compounds are pretty decent disinfectants. Okay? The difference with what I drew here, quaternary ammonia compounds usually have one of these groups that is really, really, really long. Actually, if you read the composition of like a shower gel or a shampoo, it's going to contain something like cetylpyridinium or benzalkyl or something like that. That stuff works as preservatives. Okay? All good so far? So now, I'm going to ask you a couple of questions here. So here you have ephedrine hydrochloride. Okay? Let's say I'm going to remove this. So this is your ephedrine. Okay? I deliberately crossed it out. This is the ephedrine. This is ephedrine hydrochloride. You mix ephedrine with hydrochloric acid. Hydrogen binds to that nitrogen, okay, forming a cation. You see what I'm saying? And chloride anion. All good? Now, for the point that I want to make, this is gone, sorry. Okay, good. And the same is with Benadryl. This is gone, and this is gone. So this is not an easy question that I'm about to ask. Why don't we just use straight ephedrine or straight diphenhydramine? One of the things that I want you guys to, well, not guys, but folks, to master eventually. Do not approach the problem as, oh crap, I don't know it. Approach it from the standpoint, I will try to figure it out. So how about we're going to figure it out together? When you take Sudafed or Benadryl, how do you take it? Like a pill. But is that we're going to figure it out using a bunch of stupid questions. When you take a pill, where does it go? And then intestines. The environment in the stomach and in the intestines, is it hydrophobic or hydrophilic? Water-based or not? Water-based, right? We're 60% water, right? What about the solubility of organic compounds in water? What do you think? All organic compounds? Like, remember we're talking about the properties of most organic compounds. They're not really water-loving, aren't they? Right? And moreover, remember when we were talking about alcohols, aldehydes, ketones, carbonic acids, they all have that same trope. The more carbons you have in the molecule, the less polar it is. Okay? Sounds good? So if you look at, let's say, ephedrine, this is the polar bond, and like these are the polar bonds. But other than that, you have carbon, another one, 6, like you have 9 carbons there. It is not, ephedrine by itself should not be soluble in water. But if you mix it with hydrochloric acid, it becomes a cation, right? And suddenly, you basically have a salt. With this, same story. You have a salt. So the fact that this is the salt allows you to use this as a drug, because now this cation will go in the cell and do whatever it needs to do because it's soluble in water. Now, good? Okay. I know that it's a very 180 degrees turn from Sudafed to cocaine. Okay? Now, so this is cocaine hydrochloride. Okay? It's a salt. This is the chloride 9 cation. So if you treat it with the base, like sodium hydroxide, you neutralize that Cl-, forming water, salt, and the crack cocaine, which, and come on, common knowledge, what is the administration route for cocaine hydrochloride? So again, snorting. Why? It gets to the brain faster. Remember, it's still water everywhere, so it gets dissolved pretty quickly. How else can you administer cocaine hydrochloride? Nope. That's not going to be effective. Okay, rubbing in the mouth because there's saliva. Saliva dissolves it. How is cocaine usually often transported? By the mules to get through the airport. How? Swallowing the package. And if the package breaks, what happens to that person? Immediate, because again, it's the cocaine hydrochloride. It is soluble. You didn't mention the old-fashioned way to administer cocaine. IV. Because it is a salt. But when you neutralize cocaine hydrochloride to form crack cocaine, how is crack consumed? Smoking. Because it is more efficient way to deliver non-polar substance into the lungs. Does that make sense? And interestingly enough, a lot of amines have serious biological activity. So cocaine, for instance, serotonin, okay, also. I'm blanking on melatonin, it's amine, epinephrine, or noradrenaline and norepinephrine or adrenaline. So we unfortunately, okay. So what is, if you go and try to buy Sudafed at a pharmacy, can you just grab it from the shelf? Why? Go on. Yes, exactly. It can be converted relatively simply into crystal meth. Okay? But that implies crystal meth is just better in terms of making people high. I'm talking physiology, like seriously. So, can you get high from Sudafed? Yes, you just need way more, and your liver is not going to say thank you. Okay? Here's another thing. Adrenaline. Do you like the rides, like roller coasters? Yeah. Do you like them? Okay, you do? Sure. I'm afraid of, I have phobia of heights. But you like it, and it makes you kind of happy, you know? That's adrenaline. That's norepinephrine that is released when you are in that state of excitation. There are drugs, like normal pharmacy drugs, that work in a similar fashion. One of them is phenylephrine. It's nasal decongestant. Well, guess what? People would buy it and chug the bottles of nasal decongestant, killing the liver, but it will produce that reaction. Okay? So another thing is about amines, is that many so-called alkaloids are amines. So a bit of linguistics here. Look at this word, alkaloid. In which language al is the common prefix for the nouns? Which language? Arabic. This name comes from the Arabic term al-Kali. What does that mean? What do you think? Al-Kali. Alkali. Alkaline. What does that alkaline mean in English? If I tell you that the pH is alkaline, it's a basic. So the original word alkali is an Arabic word which literally means the base, the chemical, the chemical with that property. Okay? Alkaloids contain a bunch of nitrogen atoms, which act, as we just learned, as a base. So alkaloids from plants act as a base. A lot of them are biologically active. So for instance, nicotine is an alkaloid. So is a human neurotransmitter called acetylcholine. They both are alkaloids. Nicotine stimulates acetylcholine receptors in your brain, and it works. It is a stimulant, okay? It is addictive. I'm not arguing with that. Does that make sense to you? Other alkaloids that you probably try on a regular basis are caffeine, theobromine. Anyone likes chocolate? Theobromine is an alkaloid in chocolate, and theophylline, which is a main alkaloid in tea. All of them have stimulating effects. Now let me ask you this. Do you drink coffee, folks? You do, okay. If it's super strong, how does it taste? Bitter. This is caffeine being bitter. 99% chocolate, how does it taste? That's theobromine. Super strong tea, how does it taste? Bitter. That's theophylline. Alkaloids in general have bitter taste. Nicotine in large concentrations has a bitter taste. Okay? So this is what we're talking about. That's caffeine. Okay? So it increases alertness by inhibiting, I want to say, no, I think it's antagonizing adenosine receptors. Maybe inhibiting. I don't know. But it messes up, there's a neurotransmitter basically called adenosine, which looks very similar to caffeine. So, that's that. So these are other alkaloids, morphine and codeine. Okay? So codeine is still, I think, used in some of the medications. Morphine, as you know, is a prescription drug. So we have this drug, well, both of them actually are opioids. Humans produce natural opioids. When you are, especially when you're exercising or you're scared or you're fighting someone, you produce opioids that act as painkillers in your brain. When somebody starts abusing synthetic opioids are better, more active. So, first of all, they form a habit because these cause a physical addiction, okay? Withdrawal, meaning that if there is a withdrawal, there's going to be symptoms of withdrawal. Does that make sense? Physical symptoms, that's important. It's not like, for instance, there are drugs that do not cause physical addiction. Hallucinogens, like psilocybins and LSD, they do not have physical addiction. They do not have physical withdrawal. If a person stops taking them, there are no physical symptoms associated with it. Okay? But eventually what happens, when the person abuses the drugs, like opioids, the receptors for these drugs become resistant, and the person requires more and more and greater dose. Okay? So, if someone steps away, stops taking them cold turkey, the naturally produced opioids are not strong enough, are not potent enough to provide the same level of stimulation, and the receptors are resistant. So it takes a lot of time for the receptors to become not resistant again. So far, good? Now, what would happen if you will take an amino group like this and replace one of the hydrogens with the carboxylic acid? You would get an amide. A lot of amides are also biologically active compounds. So you can consider an amide from two different angles. One angle is the one that I mentioned. You take ammonia or an amine and replace one of the hydrogens with a carboxylic group, right? Or you can consider from the other way. You can say, well, this is the carboxylic acid. What if we replace OH with NH2? Does that make sense? When you go that way, you get amides. The simplest amide is urea. Okay? Good? Now, here's the thing. Do you remember what gives this atom the properties of a base according to Bronsted-Lowry classification? What does a nitrogen have? Hydrogens, but what, like why? It's not just a place, it's something there. What is another term for two? When you put socks on, or shoes, how do shoes come usually? In pair. So what does nitrogen have to accept a positively charged hydrogen? A lone pair of electrons, right? So this is the base, this is the base. Okay? Urea is a pretty strong base. When human body processes, I'm not done with urea yet. When human body processes proteins, the final product of that processing is urea. It is a base, so if it stays in the blood, it will work as a base, increasing pH. Does that make sense? Let's say so kidneys remove urea out of the bloodstream. Okay? This is like, that's P. Okay? If kidneys shut down, urea starts to accumulate in the blood, leading to uremia. Remind me, please, if urea is the base, how does it change the pH of the blood? A base, what does it do to pH? Increases it, right? So people develop alkalosis. And in alkalosis, your neurons get overactivated. And if the neurons in your brain get overactivated, which you may develop, it's called a seizure. Okay? One of the symptoms. Does anyone use chewing gum? Yes? By chance, do you have it on you now? Yeah, I mean, I'm looking for the components. No? Okay. So, is it sugar-free? It's not sugar-free. Okay. But the chewing gum that is like, touted, like to protect your teeth, pretty much. If you use any of those, read the packaging. One of the components there will be carbamide. Carbamide is used as a base to neutralize the acid that's formed in your mouth after you had a meal. Carbamide is urea. So, yes, when you chew, it's absolutely benign. When you chew gum, there is the same chemical that is found in your pee. Okay? Another example of biologically active amides, this weird-looking barbitals. Okay? Barbiturates are sedatives. I believe luminol is used, it's stronger than nembutal. Luminol is used as the horse sedative. Okay? So this kind of wraps up our conversation about amides. We're going to take a small break, come back, and then we will both decide, all of us will decide how we're going to proceed further.